Hi there. This is a note from future John. I've come back through time to tell you what happens in this video. I should start by saying this video does not constitute a success. So we spend a lot of time doing stuff, but we don't get anywhere successful in the end. We do learn a couple of things along the way, so I'm still going to publish the video. But I just want you to know, if you watch this video, we don't succeed in the end. I am going to come back to this. What we do in this video is we look at the Epaper modules from WeAct Studio. There'll be notes about that in the show links. The first 1/3 to 1/2 of this video, we have a close look at the data sheets for one of those modules, the Epaper modules. Then we spend a bit of time setting up Arduino to load the sample program that came from WeAct Studio. We download that from GitHub. We have to install some libraries and such, so we fumble our way through that. Also, we have a look at the options for microcontrollers for this project, and we discuss a few alternatives that are available. We decide to try the ESP32-C3 microcontrollers. I have a couple of those. I take one of them and I solder some pin header. That takes actually quite a lot of time. I should have time-lapsed it for you, but I'm still I didn't know when to exactly do that, so I didn't do that properly in this video. I have learned that I need to make provisions for that, so hopefully in future videos I'll do a better job of time-lapsing the boring bits. I didn't do a particularly good job of that in this video. The only thing I time-lapse in this video is at the very end, when I do the logic analyzer hookup, which I'll tell you about in a second. The first thing to know about that pin header soldering, that didn't go well at all. I think that my soldering iron was not up to the job. I don't think it was delivering enough heat to the joints. There was plenty of good leaded solder. It had plenty of flux. I can't account for the poor joints I was getting. In future, when I'm putting on those pin headers, I'll use a mild abrasive on the and maybe some of the deoxit on some of the terminals before I try to solder on the pin headers. So anyway, we eventually sort of fobbed our way through that. I did get the Arduino IDE working sufficiently to upload the software, but I couldn't get like the debugger or the serial link print line facility to work. Yeah, I tried installing the two Epaper modules that I had. I couldn't get either of them to work. I decided in the end I want to have a look at the interface. It's either I2C or the other one. It's one of those serial interfaces. And I thought, okay, this is a good opportunity to use my logic analyzer on my MSO, mixed signal oscilloscope. So I wire in the logic analyzer. I just put 8 pins on, and then actually that's when I stop this video. I'm not going to continue down that path in this video. I will come back to this whole thing again. I'm not done with the Epaper modules. I do want to get them to work. I'm not done with the ESP32-C3s. I also want to get them to work. My logic analyzer, I still need to learn more about how to actually use it effectively. And there are also some other tools that I might like to use, including the Great FET. And I'll link you to the Great FET in the show notes for this video. I've never used the Great FET, but it does seem like it might be the sort of thing that could help me diagnose what's happening on that serial line between the microcontroller and the WeAct Studio Epaper module. So yeah, and as I say, at the tail end of the video, I just time-lapse you through the logic analyzer hookup. but yeah, this whole project's just been shelved. I'm going to pick it up again in the future. I'm probably going to try using, instead of the ESP32-C3s, I'm probably going to try using some Arduinos and getting those to work with the Epaper module. So that's probably going to be my next strategy. Anyway, look, that's everything to tell you from the future about what you're going to see in this show if you watch it. So now, let's... Hi there, you're in the lab with your mate JJ. Today is Interlude. Today's Interlude. I'm going to take a break from everything else that I'm doing and just do one specific thing. I was talking to my mate River on IRC, who mentioned about e-ink, and it got me thinking. I have some e-ink modules. I've got two of these 2.9 inch, and I've got another two 2.13 inch. So I've got two lots of two for a total of 4 e-ink displays. Someone else on IRC said that there is other memory display technology than e-ink, but this is e-ink, and it's from WeAct Studio, and it seems to me like their support and their documentation and everything is fairly good. So I've never used these before. I don't know anything about them. So I thought, first of all, what we'll do together is jump on the computer and go over to GitHub and have a look at the WeAct Studio support libraries, bits and pieces for this device. And then hopefully we can download some code, pick a microcontroller to run it on, plug this thing into the microcontroller, and then put up a hello world on the e-ink display. So before I take you over to the bench, I thought I might start you here on the computer, and we'll just see what the support from WeAct Studio is like, and then we'll pick a project, and they've got example projects, so we'll pick one of those. We'll have to pick a corresponding microcontroller. I'll show you in a minute what that means. So let's jump over to the computer and let's have a look at the software support. Here we are on the computer. Actually, I've got a book here. I'm just going to move this. See, I've got my cool little. Can you see that? Yeah, it's my book holder. I've been working through God Created the Integers by Stephen Hawking, and it's taking me ages. I've been working on it for weeks. So I've got to get that finished, but it's going to take me a little bit longer, so I thought I'd do some other videos in the meantime. So yes, here we are on the computer, and we're just going to look for WeAct Studio Epaper. There we go. And there it is. I've been there before. So looks good to me. So let's see what they've got by way of documentation. Maybe we'll just get the whole lot, huh? So I'm just creating some I'm just going to get the Git repository. Why wouldn't I do that? So just cloning that Git repository now. We've got a Alright. Oh, that's interesting. I've got it on my desktop as well. Alright. Well, I'll just move that over there. So let's get out of there. So there's a Git folder on my desktop there. Very good. So what are we going to do? I'm going to go in here, in here, in here, and I'm going to move that over to here. Very good. And the other thing I might do is going to delete this. Alright. Is that what I wanted to do? Yeah, okay. I usually have my my Git stuff there, so I'll just leave that little symlink there for the future. Alright, so here's the documentation. 1, 2, 3, 4, 5, 6, 7, 8. 8 documents. This is for 4.2 inch. Okay, that's not what we have. SSD 1680. EPD, I'm going to guess that's Epaper display. What do you reckon? Okay, so this was updated last 2019, 5 years ago. I'm trying to see the dimensions. Maybe you saw the dimensions on the way through. So I'll put that way you can see it. Well, this all means almost nothing to me, and I think it's much lower level details than I'll need. There's probably a library that I can use which will make it a lot simpler than having to know about all of this that it's showing me. Let's just close that. Let's jump down here. Okay, that's some sort of a connector. I wish it would tell. Oh, there we go. This is the 2.13 inch. Shall we just use the 2.13 inch? I wonder if there's one for the... This is the 2.9 inch. Very good. I wonder what this one is. .54 inch. There you go. So I think this is the one that we want. I think we might read this whole thing. That's going to take a little while. but why not? Let's do it. So this is the documentation for the 2.9 inch, which is this, by the way. Can you see that? Yeah. It's the WeAct Studio 2.9 inch Epaper module. Doesn't seem to have any version number or anything on it. Maybe in here. Hey, let's jump over to the bench together quickly and have a look at the device. Then we'll come back here and we'll read this. Here on the bench, this is our WeAct Studio 2.9 inch Epaper module. Now it looks like we've got a little clip here. See if we can get that open. There we go. Alright, so it's in a little bit of bubble wrap there, very good. This is much smaller than I had imagined from what I saw in the documentation. Did you notice the documentation for this cable? We opened that just a minute ago. I saw this part. So there we go. We've got some DuPont females through to this little connecty thingo there. And we've got 2x4 jumpers or headers. Okay, so I'm going to just put the plastic bag away. We might put him back in that later on. Alright, so this says 2.9 Epaper module. Can you see that? 2.9 Epaper module designed by WeAct Studio with 296 by 128 resolution. Hello world. And then we've got weactstudio.taobao.com and weactstudio.aliexpress.com. There you go. Obviously I've used AliExpress quite a lot. I've never used Taobao, so I don't know much about them. And on the back, it doesn't have... Oh yes, there we go. Oh no. I thought we had a version number there for a second, but we don't seem to have. So there you go. Now we've got our connector, which is all well and good, and then we've got our pin headers, which we could alternatively use. So this is a pretty cool looking bit of kit. I think that instead of messing around with jumpers, let's just plug this in and take it from there. So is this going to be easy or is it going to be hard? I'm not sure if that's going in. I think what I want is some pliers. Yeah. Yeah, that seems to be in. Seems to be in. Alright. Well, we've got Busy, Res, DC, CS, SCL, SDA, Ground, and VCC. Alright, so that's our board. Now let's jump back over to the computer in RTFM. Here we are again on the computer. So, did you notice... was it this one? Yeah, there you go. So this is the documentation for that little connector that they've got on the back of the board, and they gave us a cable that goes with it, so that's all well and good. Great. So this is the OEL display module. Okay, notes. Please contact the manufacturer before assigning your product based on this module specification. The information contained herein is presented merely to indicate the characteristics and performance of our products. No responsibility is assumed for any intellectual property claims or other problems that may result from application based on the module described here in. Alright, update mechanical drawings. Oh, there we go. So first version 2021 and an update in February 2022. That's great, that's fairly recent, just a couple of years ago. Alright, so we've got overview, features, mechanical specifications, mechanical drawing of EPD module. Now I'm guessing that EPD is electronic paper display. That's my guess. Maybe it'll be clear later on. Input-output pin assignment, electrical characteristics, absolute maximum rating, panel DC characteristics, panel AC characteristics, MCU interface selection, MCU serial interface, 4-wire SPI, MCU serial interface, 3-wire SPI, interface timing, command table, optical specifications, handling, safety and environment requirements, reliability test, block diagram, typical application circuit with SPI interface, typical operating sequence, normal operation flow, normal operation reference program code, part number definition, inspection condition, environment, illuminance, inspection method, display area, inspection standard, electric inspection standard. Oh dear, I'm out of coffee. I'm going to go and get some coffee. I'll be right back. I'm back and I have my coffee. So let's skip over the table of contents. It was pretty much finished anyway. This is the overview. So this product is an active matrix electrophoretic display, AMEPD. There we go. So it's not electronic paper, it's electrophoretic. AMEPD with interface and a reference system design. Okay, great. The display is capable to display images at 1-bit white, black, full display capabilities. It looks like the English in this manual is not going to be super good. That's okay. The 2.9 inch active area contains 296 by 128 pixels. The module is a TFT array driving electrophoresis display with integrated circuits including gate driver, source driver, MCU interface, timing controller, oscillator, DC to DC conversion, static RAM, LUT. I don't know what that means. Usually it's something under test. VCOM. I suppose VCOM is just voltage, I'm not sure. Module can be used in portable electronic devices such as electronic shelf label system. Cool. You can use them as the labels on a shelf. That's cool. Very cool. Shall we look up TFT? I feel like I should know what TFT I should know what TFT stands for. Oh, there we go. Thin film transistor. Okay. The module is a TFT array. Okay, great. So the signal comes in through the thin film transistor array, and then that drives the EPD, which is the electrophoresis display. Cool. So features: 296 by 128 pixels display, high contrast, high reflectance, ultra wide viewing angle, ultra low power consumption, pure reflective mode, bistable display, commercial temperature range, landscape portrait modes, hard coat anti-glare display surface, ultra low current deep sleep mode, on-chip display RAM, waveform can be stored in on-chip OTP or written by MCU. OTP, I always think one-time pad, but that's not. This is some sort of like one-time password, do you think? Waveform can be stored in on-chip OTP or written by MCU. OTP, it's not one-time password. OTP on the phone. Isn't that funny? Alright. On that point, over temperature protection on the phone. Yeah, I don't know. Not getting a good read on that at the moment. Maybe it'll become clear later on. Alright. Serial peripheral interfaces available. On-chip oscillator, on-chip booster and regulator control for generating VCOM. I think that means the common voltage, like yeah, whatever it is, 5 volts probably. Gate and sourcing driving voltage. I2C signal master interface to read external temperature sensor. Fascinating. Built-in temperature sensor. Okay, so it's got a built-in temperature sensor, and can it either read another one or provide an interface to the one that it has? I'm not sure what that means. Mechanical specifications. So as we know, it's a 2.9 inch display. Resolution, we've already covered that. Active area in millimeters, so 3 centimeters by 6 centimeters roughly. That's the size of a pixel, about 0.22 of a millimeter. Rectangular configuration, outline dimensions, weight, not very much, about 6 grams. Here's some technical drawings, very good. There's not much to it, is it? It's really thin. Great. Alright, now there's the pin out for the oh dear. I wonder if we can. Might just see if I can bring up an extra screen. Bear with me for a second. Alright, I'm back, and I've added this little camera you can see here up the top right hand corner of the screen there. You can see across the top here, do you see that? Those are the pins that that this PDF here is talking about. So that's for this part of the interface here. But we don't need to deal with the complexity of that. It gets changed into these eight pins over here. So this is our interface on this side of it, and this is the bit that talks to the screen. Fair enough. So I'll put you back over to the normal view, and we'll keep on keeping on. So, do we want to read all this? Why not? NC, do not connect with other NC pins. Keep open. GDR, it's an output pin. N-channel MOSFET gate drive control. There you go. RESE, it's input signal. Current sense input for the control loop. NC. I think NC just means no connection. No connection. Or maybe not. NC. Oh yeah, it is. It's just NC, not connected. Okay. Okay, not connected, and don't connect with other NC pins. You don't connect with anything. So keep open, keep open. Okay, we've got 5 VSH2C. I wonder what C means. Positive source driving voltage. IO, C for current maybe. I'm not sure. TSCL, it's output pin. I2C interface to digital temperature sensor clock pin. Okay, cool. And then TSDA, input and output. I2C interface to digital temperature sensor data pin. Okay. BS1, it's an input bus interface selection pin. Busy signal, it's an output, busy state output pin. That's actually, that goes through, that's actually in the 8 pin. Okay. There's res number, that's the same, it's input, reset signal input active low. Okay. D/C. This busy, res, and DC, all of those actually come through on the. I wonder if I can show you in enough detail. Sorry, I'll just transition you over so you can see me fiddling around with this. Can you see that? I'm not sure if it's large enough on your screen, but this top one, that's the busy signal, and the next one is the res signal, which is the active low reset signal input, and then there's D/C, which is an input signal as well. That's pin 3 here. That stands for data/command control pin. And then there's CS. It's an input, and that's also here. That's the 4th pin here. CS is the chip select input pin. Then we've got SCL, again, serial clock pin. It's input. SDA, it's input output serial data pin. SPI1 or SPI. Oh, okay, cool. So, okay. So that I2C interface is for the thermometer, but this interface is SPI, and these are the SPI pins here. And then we've got the SDA pin, which is again here. That's pin 6, SDA, which is oh, we already discussed that, of course. Serial data pin. And then we've got ground and VCC. Okay. So now we're back over here. We're up to pin 15. Again, this is on the back end. So these don't concern us, but we'll read about them anyway. So we've got pin 15, VDDIO, P. I assume power. Yeah, power supply for interface logic pins. It should be connected with VCI. Okay, so there's VCI, also power supply. VSS. Okay, that's the ground. Very good, ground pin. And then VDD. C for current. I'm not sure. Core logic power pin, VDD, can be regulated internally from VCI. Okay, great. A capacitor should be connected between VDD and VSS. Okay, cool. VPP. Okay, that's a test, forward test. Is it power forward test? I'm not sure. VSH1, C, positive source driving voltage. VGH, C, power supply pin for positive gate driving voltage and VSH1. VSL, C, negative source driving voltage. VGL, power supply pin for negative gate driving voltage, VCOM and VSL, and VCOM is VCOM. I suppose that's voltage common, I'm not sure. Oh, here we go. We've got a legend, that's great. Okay, cool. So I is for input, O is for output, I is for input and output, P is for power, C is a capacitor pin. Capacitor pin. So you have to put a capacitor. Is it just a decoupling capacitor? I'm not sure. Note 5.1. So this is the note for chip select input. This pin, chip select, is the chip select input connecting to the MCU. The chip is enabled for MCU communication only when CS is pulled low. And then note 5.2, the pin DC, data command control, connecting to the MCU in a 4-wire SPI mode. Okay, when the pin is pulled high, the data at SDA will be interpreted as data. When the pin is pulled low, the data at SDA will be interpreted as command. Cool. The res pin is the reset signal input. The reset is active low. And then the busy pin is an output pin. When busy is high, the operation of chip should not be interrupted. Command should not be sent. The chip would put busy pin high when outputting display waveform or communicating with digital temperature sensor. Right. Bus interface selection pin. Okay, so you can choose whether you want the 3 lines or the 4 lines. And if you put BS1 low, you get 4 lines, 8 bits SPI. And if you put it high, you get 3 lines, 9 bits SPI. There you go. Now, I don't think BS1, yeah, there's no choice here. So that looks like they've made a decision on the board about that. I'm not seeing BS1 on the I/O that we have. Yeah, it's just before the busy signal, which is the first one we get. So that BS1 isn't available to us. So I'm going to guess and say that they're using the 4-pin SPI bus, and that will be, presumably, if we go up here, it'll be SCL, SDA, and then one of these voltages, and ground. That'll be 4 wires. Power, and then the clock and the data pin. So I don't know what 3-wire is. I'm not sure what they don't include. Maybe they don't include power, I don't know. Electrical characteristics, absolute maximum rating. So logic supply voltage up to 4 volts. Okay. And no less than negative half a volt. Logic input voltage up to half a volt either side. Or to VCI plus, okay. So, okay, to VCI, the operating temperature can go up to 50 degrees Celsius. Storage temperature can go up to 70 degrees Celsius. Optimal storage temp is around room temperature. And humidity is, okay, so 55 plus or minus 10. Maximum ratings are those values beyond which damages to the device may occur. Functional operation should be restricted to the limits in the panel DC characteristics tables. Very good. Okay, the following specifications apply. VSS is 0 volts, it's our ground signal. VCI is 3 volts. And TOPR, so that's typical operating temperature, 25 degrees Celsius. Alright. So VSS 0, logic supply up to 3.7 volts, core logic voltage up to 1.9 volts, high level input voltage 80% of VCI, okay. Low level input voltage, high level, low level, typical power 9 milliwatts, deep sleep mode 0.003 milliwatts, typical operating current 3 milliamps, image update time 3 seconds. Fascinating. Sleep mode current 20 microamps. Deep sleep mode current is 5 microamps. Very good. The typical power is measured with the following transition from horizontal 2-scale pattern to vertical 2-scale pattern. Okay. The deep sleep power is the consumed power when the panel controller is in the deep sleep mode. The listed electrical and optical characteristics are only guaranteed under the controller and waveform provided by us. I suppose that's us. Okay, so these are the AC characteristics. Microcontroller interface selection. The pin assignment at different interface mode is summarized in table 641. Okay. Different microcontrollers can be set by hardware selection on BS1 pins. The display panel only supports 4-wire SPI or 3-wire SPI interface mode. Okay, and then we've got the pin name and the data command interface, and then the control signal. So that looks like the does the L just mean it's pulled low and it's not used? I don't know. If the data and control pin is not available, how does it send data and control information? I don't know. MCU serial interface, 4-wire SPI. The serial interface consists of a serial clock, SCL, serial data, SDA, data command pin, and CS pin. What was CS pin? Chip select, maybe? Chip select input pin. Yeah, very good. Alright. So, where were we? Here. Okay. This interface supports write mode and read mode. So write command, low, low, and send. Write data, low, high, and send. Note, up arrow stands for rising edge of signal. In the write mode SDA is shifted into an 8-bit shift register on every rising edge of SCL in the order of D7, D6 to Z to D0. The level of DC should be kept over the whole byte. Okay, the data byte in the shift register is written to the graphic display data RAM / data byte register or command byte register according to the data / command pin. So this is chip select, and then this, which is active low by the looks of it, and then this is data / command. So it's okay, and then there's the clock pulse train, clock, and then this is the SDA write mode. Okay, there you go. So this is in write mode. In read mode, after driving CS low, the microcontroller needs to define the register to be read. SDA is shifted into an 8-bit shift register on every rising edge of SCL in the order of D7 to D0 with DC kept low. So we've got a diagram of this here. After the clock changed to low for the last bit, DC need to drive to high. SDA is shifted out an 8-bit data on every falling edge of the clock in the order of 7 to 0. That's bits. Depending on register type, more than 1 byte can be read out. After all bytes are read, chip select need to drive to high to stop the read operation. Okay. So in the 3-wire mode, it seems like you can't distinguish between data and command. The 3-wire signal interface consists of a serial clock, serial data, and chip select. This interface also supports write mode and read mode. Okay. The operation is similar to 4-wire serial interface, while the data / command pin is not used. There are altogether 9 bits, which will be shifted into the shift register on every 9th clock. That means one of the bits. Look at that, that's the DC bit. Very clever. Okay, great. So they're basically not using the DC pin, they're using a DC bit. And instead of having 8 bits, they've got 9 bits. That's cool, and you can save yourself a whole wire. Okay. It would affect your bandwidth, obviously, but only a little bit. Very cool. The DC bit, first bit of the sequential data, will determine the following data byte in the shift register written to the display data RAM or the command register. Yeah, great. Okay, that's really cool. There we go. 0 and 1. So in read mode, after driving, it's active low, so CS to low. The microcontroller needs to define the register to be read. The data / command bit is 0. Is shifted through SDA with 1 rising edge of the clock. SDA is shifted into an 8-bit shift register on every rising edge of SCL in the order of D7 to D0. Then DC equals 1 is shifted through SDA with 1 rising edge of SCL. SCL is the clock, of course. SDA is shifted out to an 8-bit data on every falling edge of the clock in the order of D7 to D0. Depending on register type, more than 1 byte can be read out. After all bytes are read, CS needs to drive to high to stop the read operation. There you go. Interface timing. The following specifications apply. VSS 0 volts, VCI 3 volts, TOPR. So that's a temperature. It's room temperature. Okay, well, we're not interested in all of those timing details. They're not going to matter for us. Presumably we're going to interact with some sort of library, but we haven't seen that code yet, but we'll find it. Here's the command table. Okay. Gate setting, gate scanning. Oh dear. Booster soft start control. Deep sleep mode. Data entry mode. Software reset. HV ready detection. HV, is that high voltage maybe? I'm not sure. VCI detection. Temperature sensor control. Temperature sensor control. Write to temperature register. Read from temperature register. It's interesting that it's got temperature capabilities. That seems above and beyond, doesn't it? Above and beyond the Call of Duty, I mean. Display update control. Display update control 2. Write RAM, black or white RAM. Write RAM, read RAM. VCOM sense. Enter VCOM sensing conditions and hold for duration defined in 29H before reading VCOM value. The sense VCOM voltage is stored in the register. Command required. Clock enable and analog enable. Refer to register 22 for detail. VCOM sense duration. Program VCOM OTP. And we didn't figure out OTP. I don't think it's one-time password, so I'm not sure. Write register for VCOM control. Write VCOM register. OTP register read for display option. User ID read. Status bit read. Program WS OTP. Load WS OTP. Write LUT. CRC calculation. CRC status read. Program OTP selection. It would be really good if we knew what OTP stood for. If you know, please let me know. Write register for display option. Write register for user ID. OTP program mode. Border waveform control. End option. Read RAM. Set RAM. Set RAM Y. Auto write red RAM for regular pattern. Auto write black and white RAM for regular pattern. Set RAM X, set RAM Y. No op. There we go. Alright, optical specifications. Measurements are made with the illumination under an angle of 45 degrees. The detection is perpendicular unless otherwise specified. So there's a bunch of specs about the optical specs. Handling, okay, warning, the display glass may break when it is dropped or bumped. Handle with care. Should the display break, do not touch the electrophoretic material. In case of contact with the material, wash with water and soap. Caution, the display module should not be exposed to harmful gases, such as acid and alkali gases, which corrode electronic components. Disassembling the display module. Disassembling the display module can cause permanent damage and invalidates the warranty agreements. Observe general precautions that are common to handling delicate electronic components. The glass can break and front surfaces can easily be damaged. Moreover, the display is sensitive to static electricity and other rough environmental conditions. Okay. So, okay, these are the testing the test that they did for reliability. Okay, and again, this is the other end. So the end that we have is this end, but the end that they're talking about there is that end, and we don't have to concern ourselves with that. But that's what's on this screen here. So that comes out, and then onto the driver PC board. Temperature sensor circuit. I'm not sure if that's on there or not. I don't know. Maybe we'll have a look at that. There's a microcontroller circuit, the capacitor circuit, DC to DC circuit, and power circuit. So that DC to DC, I assume that's just a voltage regulator of some sort. Typical application circuit. Okay, so it's going to come with something like this on the motherboard. That's what we're dealing with. There we go. And here are the pins here. Ah, okay, cool. So you can connect it to an external temperature sensor, but it has one on board, so I don't think you need another one. These are the pins that we have. There's VSS, and there should be VCC somewhere as well. Anyway, okay, great. So it's something like this circuit is on the on the board here. That's what that is. Something like this. Okay, normal operation flow. Power on, and supply VCI. Wait 10 milliseconds. Set initial configuration. Define SPI interface to communicate with the controller. Hardware reset. Software reset by command 012. Wait 10 milliseconds. Send initialization code. Set gate driver output by command 1. Set RAM size by command 11, 44, and 45. Set panel border by command 3C. Load waveform LUT. Sense temperature by either the internal or the external temperature sensor by command 18. Load the waveform LUT from OTP by command 0x22, 0x20, or by MCU. Now I don't know what LUT means, and I don't know what OTP means. So let's see. Actually, you know what I might do? Okay, what I'm going to try and do is ask ChatGPT and say, in electronics, what does OTP and LUT mean? One-time programmable and lookup table. Okay, cool. One-time programmable refers to a type of memory. Let me just move this over here so you can see it. OTP refers to a type of memory or storage that can be written to only once. Once data is written to an OTP device, it cannot be altered or erased. OTP memory is often used for storing critical configuration information, such as device calibration data or security keys, where data integrity and performance are crucial. That's data integrity and permanence are crucial. Common uses of OTP include firmware storage in microcontrollers or other embedded systems. For example, an OTP ROM, a read-only memory, is used in some microcontrollers where once the data is written, it is not modifiable. An LUT, lookup table. A lookup table is a data structure used to store pre-computed values or results of computations, often to speed up complex calculations by replacing them with simple table lookups. In digital electronics, LUTs are used in programmable logic devices such as FPGAs, field programmable gate arrays, to implement combinational logic, An LUT allows a device to implement any Boolean function of its inputs by storing the function's output values in a table. For example, in an FPGA, a 4-input lookup table can store the output of any Boolean function with 4 inputs. This enables the FPGA to implement complex logic operations without requiring more traditional logic gates. In summary, OLTP refers to non-erasable memory used for storing permanent data, and LUT is a pre-computed table used to speed up logical operations or computations in digital circuits. So that makes this clearer now, doesn't it? So where does it do that? Okay, load waveform lookup table from the OTP by command. Okay, so it looks like you can write in onto the display and then burn in a default screen that will get shown from the lookup table as soon as it turns on. That's my guess. Then you can write, so then once we get to step 5, we can write the image data into RAM by these 4 commands, and then set soft start, and then drive the display panel, and then wait, and then power off. You can deep sleep and it can power off, and you can power on again, and you go through the whole boot cycle if you do that. Okay, normal operation reference program code. TBD. Okay, so the code looks like it hasn't been written yet, but it's probably in the example project. Part number definition, not done. Inspection condition. Okay, so there's its various angles. Okay, it's just environmental stuff. Okay, bits and pieces about the okay, electric inspection. Okay, so this is okay. Ghost image. Yeah, right. Okay. I don't think we care about that performance detail at this point. Okay. Alright, well, now we know a little bit about the hardware. Oh, what's in here? Wonder what SCH. Oh, this is the schematic. This is the schematic for the board. Now, I wonder, do we have the thermostat, the temperature? Did we see one of those? I'm not sure. What pin did they say it was on? We go back over to this documentation. Just looking for what pin the external there we go. TSCL. So we got TSCL in here anywhere. What pin number was it? 6 and 7. 2, 3, 4, 5. 6 and 7. Okay, well pin 6 is not connected. Oh, maybe it is. 1. Okay. Well, it seems to me like pin 6 is not connected, and pin 7 has a capacitor. Okay. So it's just going to use its internal thermometer, I guess. Fair enough. And I'm going to take a quick break and I'll be back in a minute. I'm back. I just had a bath and a breakfast and all sorts of things, so I've been gone for a while. Of course, you don't know that. So I think we finished with our schematic. And this schematic, and we just showed that pin 6 and 7 for the external temperature aren't used in this reference circuit. Fair enough. There were some other documents here, so let's see if we can figure that out. What was this? Yeah, right, that was the connector. And what one was this? Oh, this was a different model. This is the 4.2 inch. It's a really big one, I guess. Then we've got various examples for different boards, hardware. Now that was the schematic that we just had. Okay, cool. So the 2.9 inch. Let's have a look at that. Oh wow. 3D step. Open cascade. Shape model. Wow. And then here's some other tech drawings of the hardware. Cool. Very cool. Now I'm not sure what software you need for the 3D steps here. Perhaps the Open Cascade model, as the name suggests, is some sort of open standard. That's cool. The images we've seen, but I'll just show you them again. There's the this is the 2.9 inch one that we'll be using, and there's a little one, and there's a big one. Cool. And tools, there's something here in Japanese, or not Japanese, Chinese probably. Okay, they're various documents, but they don't appear to be in English. Look, there's a PC to LCD application notice. Okay, well, I can't read that. What about this? Nope, I can't read that either. I could have it translated. Do you want to translate this together? Oh, it's too big. That's what she said, right? The first beta version was released in the early morning of May 1st. Function introduction. 1. Generate character model data of strings mixed with Chinese and English numbers. 2. You can choose the font size and adjust the length and width of the text independently and generate characters of any shape. 3. Various rotation and flip text functions. 4. Arbitrarily adjust the size of the output dot matrix and arbitrarily adjust the position of the characters in the dot matrix. The font data output can be customized in various formats, and the system presets 2 formats of C language and assembly language, and can be its own define. I'm not sure what it's talking about here, if it's talking about a software library or if it's talking about the hardware itself. I'm not sure. Anyway, let's go over to the example directory. Now these are our options. Arduino, ESP32, I can probably do that. Yeah, these other ones don't mean anything to me. But the ESP32, I've got a couple of those free. What happened to our trusty old ChatGPT? Let's say, please, actually what I might do is just open a terminal here, and then ls, how about ll? Alright, now please tell me about the okay. Okay, this has a summary at the end. APM 32F103, GD32F103, and CH32F103. These microcontrollers are ARM Cortex M3 based and are often used for cost-effective embedded systems with basic peripherals. ESP32-C3 offers Wi-Fi connectivity but with less processing power compared to modern Wi-Fi solutions like the ESP32 series. ESP32 and ESP32-C3 are more powerful than the ESP8266, offering dual-core ESP32 or single-core ESP32-C3 performance with integrated Wi-Fi and Bluetooth support, making them ideal for IoT projects. AT32F403A and GD32F303 are high-performance ARM Cortex M4 based MCUs suitable for more demanding tasks like motor control or DSP. DSP, of course, is digital signal processing. CH32V103 based on RISC-V, offering a cheaper and more open source alternative to ARM Cortex M3 for general embedded applications. These microcontrollers are suitable for a wide range of embedded applications, from basic control systems to more complex communication and signal processing tasks, with different trade-offs in terms of power, cost, performance, and peripheral support. Alright, well, I'm going to take a minute. I'm going to go rummaging through my drawers and see what microcontroller I can dig up. I'll be right back. Okay, here we are back on the bench. I've just been taking stock of my ESP32 situation. Just between us, I have never used an ESP32. I've used plenty of Arduinos. I think this is an Arduino Nano. So I've used plenty of these Nanos, and the bigger ones, the Uno and the Mega and whatever, but I haven't used the ESP32s yet. But I do have a whole bunch of them, so let me show you what I've got, and then we'll have a think about what it is that we're going to do. So I'll see if I can find everything. I honestly don't know what we're dealing with. These are not ESP32s, but they're STM32s. Also from WeAct, who are the people who made the Epaper thing. My mate K-Line on IRC has used some STM boards. I don't know much about them myself, so we won't be using these, but I thought I'd show you that they're there. So the rest of the boards on this table, I believe, are all various types of ESP32s. Now these ones here, these are labelled ESP32 with camera. So both of these have got a little camera module. I might as well pop him out of the bag. So we can see. Now I got these from Amazon, and they came as a 2-pack. So and they come as a 2-pack with this camera module. Look at that. So it's a can you see that? It's a camera that you can plug into here. The thing is, I don't know how to program this board because it doesn't seem to have a USB port, which is ordinarily how I would interface it with a Arduino IDE. So I don't know how you program this guy, but it does seem to take a SD card, so maybe you just build an image and put it on and then you're away. I don't know. So we've got those two in there, but they don't look as promising just because there's no USB ports. Now the rest of them do have USB ports. This is a ESP32 WROOM32 WSW room. It doesn't seem to have a SD card reader, but it does have a USB micro, or is it? Yeah, USB micro. Okay, and I got a swag of these. There's two lots, the AN4 and the AN8. These are ESP32-C3 So I'm not sure really what that means. There's two types in here. One is AN4 and one is AN8. Okay. So this says ESP32C6W room 1-1, whereas this one says ESPW room 32. Okay. Now these ones look tiny. These are ESP32C3 F4H. So I think we saw that earlier. The C3s only have single core. I wonder if we can bring up the microscope. How do we do that? What are we looking for? Just gonna put the There we go. Alright, so I'll just I'll flip you over to the microscope, and let's see what we can see. So this is the ESP32-C3 FH4. Can we read that? ESP32-C3. Okay, cool. Well, we do have a thing for this board, don't we? So maybe we'll use this board. The only one that we didn't look at together is this one, which looks like it's in an Arduino Uno form factor. I'm going to throw you back over to the other view. This is the board that I'm talking about. It says that it's an ESP32-F, so I'm not sure about that, how that works. It seems to be Arduino-ish, compatible-ish. So there's all of our options. I think that we're going to go with this guy here, which is the WeAct ESP32-C3 FH4. That sounds pretty good to me. I don't know how to program these ones that just take the memory card. I should perhaps look into that, but we don't need to do that today. So here is the ESP32-C3. So I should be able to get that to work, I reckon. Now, let's just see what we can do here about USB cables. Got a whole bunch of them. Alright, this one, that's a micro, USB micro, which is exactly what we need. So that's the black cable is the USB micro, and just for the sake of completeness, the other ones, okay, the other cable is USB type B. So this is USB micro, which will, oh, no, this is a USB-C. How annoying. Okay, what about this? Also USB-C. Alright, well, let me go and dig up a USB-C cable and we'll use that for testing. Just a second. I'm back and I found this. So this looks like it'll give us a USB-C interface. I'm not sure if it's just power. It's only got a white. It's only got a white thing, so I don't know if it does USB 3 or not. I'm not sure. Anyway, let's plug this thing in. I'm just going to need some light. Here's some light. Alright. Well, there's only 2 sockets there, so let's take the top one. Alright. So now we've got a cable. I'll just run it around the back here. Okay, now we've decided to go with the ESP32-C3. So I'm going to put everything else away. I'm going to take those headers though, we might need those. And these are my ones from Amazon that don't have a USB adapter. Alright. So Alright, well I'm going to throw you over to the computer. I'm not going to plug this in just yet. We'll come back later to plug this USB-C into this ESP32-C3. But before we do that, let's just jump over to the IDE and I'll show you what we're dealing with over there. Alright, here we are on the computer. Now, I suppose I should tell you what I've done. Actually, I might even... So, here you can see we're in the... this is... I don't know why they got rid of... I don't even know how to use Windows anymore. It used to be there was a tree view over here and you knew where you were. Oh dear. Alright, so here we are. This is the there it is. There's the ESP32-C3. That's what we've got. So I'm just going to take this one and copy it, and then I'm going to put it somewhere. AVR dude? What's that? I don't know. Documents. Arduino. Alright, well I'm just going to paste it here. So this is in my Arduino documents. Fine. So I've taken a copy of that now. Needs to be inside a sketch folder. Oh, okay. Didn't like that. So let's just see what it's done. Yep, okay, great. Alright, so this is the example code for the ESP32-C3. Now we haven't plugged in a board yet, so okay, when we plug it in it should turn on, but first I want to just see Boards Manager. This is the Arduino ESP32 boards. So that's probably, I'm guessing, what we need. I've got the AVR boards already installed and I haven't put the ESP32 boards in yet. Embed OS Edge, Giga, Nano, Opta. I don't know about all this. Mega AVR boards. Okay. NRF52 boards. Uno R4. SAMD, Arduino robots, Atmel AVR explained, AT Tiny, ESP32. Okay, well that looks like it would be an option, doesn't it? Have they got they do. This is the C3, ESP32-C3. So that looks like another option. And a bunch of deprecated stuff down the bottom there. Alright, well let's install the Arduino ESP32 boards. Let's click more info and see what it has to tell us. So it's running in the background here, doing various processing. Do you want to allow apps? Sure, what's the worst that could happen? Okay. Okay, that all seems to have just installed. So I might just close this. Now this was more information. It just sent us to the home page. Okay, fair enough. So, let's open the IDE. And it says that we've got the boards installed. Okay, we've got COM1 and COM3. Now I'm going to plug this thing in. Let's see what happens. Well, the blue light came up on the board, so it's got power. Oh, restart. Okay, it needs to reboot. Alright, I'll be back in a minute. Alright, so we've rebooted. Now let's jump into... where did we keep it? Documents, Arduino, Epaper test. Alright, let's see what happens. Alright, select board. Oh, cool. Okay, it's LOL Lolin C3 Mini. Alright. The ESP32-V 3.0.7 core has to be installed for the currently selected board. Do you want to install it now? Yes, I do. Oh, there we go. We saw this earlier. So the Arduino builds on top of this bit. Great. Taking a while, isn't it? Wonder what it's doing. I'm not sure how much longer we're going to wait. Should I time-lapse this? Maybe I should. Maybe I will. Alright. Well, that'll seem to work pretty well. So let's close this and open it again and see how we're doing. Okay, that's got the board there. Oh, okay. So it's changed from Lolin C3 to ESP family. Okay. Well, let's see if we can just burn this as it is straight onto that board. Is that board... Okay, it's flashing a light on and off, 1 second on, 1 second off. So let's see if we can, well, first of all, can we compile? No, we can't. Okay, it's looking for partitions CSV. I'll be back soon. Okay, I'm back. So yeah, we tried to compile this thing and it didn't work with the system cannot find the file specified. So we seem to be missing this partitions.csv. So the first thing I might try to do is jump over to, how do I open a new tab? Oh, there it is. Okay. And we want to go into Home, Repo, Git, GitHub, WeAct, Epaper module, example. Now we're using ESP32. Okay, there's build clean. So I don't know what this partitions.csv file is. Alright, give me a second. I'm back. So we're trying to figure out this problem with the partitions CSV file, and it doesn't seem to be available. It's looking in the project folder. It's not there. So I'm really not sure where we should get this from. So let's ask ChatGPT. Okay, it's used for ESP32 boards. To define how the flash memory of the microcontroller is partitioned. If your project or board requires this file, you can obtain or create it through the following methods. Okay, so the default is included. Located in your Arduino. Okay. You may see predefined configurations. Interesting. Let's run command and let's go for that center h colon cd repo git. I never use Windows anymore. Anyway. Okay, it's not there. Now, where did it say? OneDrive documents. Okay, not found. No CSV files anywhere. I wonder where... Okay. So there is well, let's try and find it. So let's bring that down there, that up there, and open here. So C colon users JJ5. What are we looking for? Local settings, view, show hidden items. Where is local settings? I'm not seeing it. Show. It says here very clearly, directory C uses JJ5 local settings. So where is it? It's there, it just won't show it to me. Application data. Again, it's not here. Anyway, what's this? Application data, application data, application data, application data. This is insane. Arduino 15. And packages. ESP32. Tools. What about hardware? ESP32. Okay. Platform.txt. What are we looking for? Petitions. Can I open a command window here? Windows doesn't let me do any of the things that I want to do. Let's see if we can copy that. There we go. All right. So hardware and tools. All right. I'm not sure which one I should use. It did say that there was other types, didn't it? Default CSV, minimal CSV, and huge app CSV. If the project, you can create a new file. Ah, shit. Okay, let's try that. Well, let's just get a copy of it. I'll do that on a different computer. I'll just flip you over. Here I am on the other computer. I'm just going to get that that repository. Copy. Alright, now cd desk git GitHub. Okay. Now all right. Alright, so we're just cloning the Espressif Arduino ESP32 project. It's going to take a little while by the looks of it. So can you search? I don't know if you can search with an asterisk. There we go. There's the default CSV in the partitions file. Okay. Wonder if we can get one specifically for our board. Let's keep that running and let's just jump back over here. Now there's well, let's duck in here. Repo, git, GitHub, Espressif, Arduino. I forget where it said. Tools petitions. Tools petitions. Default CSV. Let's copy and let's paste it in here. And let's change it to partitions CSV. Alright, now let's go back to the Arduino and let's try building again. Tools, sketch, compile. Alright, well, we got past that first problem. Now we've got a different error. So let's open him up. I'm just going to save this as I'm going to put it desktop error.txt. Alright. So we seem to have bootloader.bin. build.mcu. Alright, well, where is that? Doesn't seem to be in here. Maybe I need to yeah, this looks right, doesn't it? ESP32-C3. Let's try that. Okay. So we're trying to include a header. Okay. Let's see if we can search in the libraries for this header. No. Well, what will ChatGPT tell us? Oh, there we go. So maybe if we just get rid of that BW. There we go. That looks like it. Let's install that. Okay. Install all. No such file or oh, that was an earlier message. Okay, well that got installed. That's good. So let's close this guy and try again from the top. So oi oi oi. So let's go. Okay, ESP32 dev module. That looks good to me. Seems to be working. I don't know how long it's going to take. I'll make that bigger and shut you off. Alright, so this is running G++. That sounds like the GNU C++ compiler, maybe? I don't know. So it's hard to see what it's doing here. It'd be good if it word wrapped. Tools. How about preferences? Preferences. Alright. Oh, there we go. So it's the OneDrive. Alright. Well, it's about halfway now, according to the little thing down the bottom here, which you can't see because of me. So I'm going to pause it. I'll come back when it's finished. Alright, well that's done compiling, and it seems to have worked. Now, I haven't pushed it onto the thing, so let's see if that'll work. Let's upload and see what happens. Fingers crossed. Wow. Error. So packet content transfer stopped. Let's throw that into ChatGPT and see if it can tell us anything about the problem. Alright, you know what I'm going to do? I'm going to use a different cable. Give me a second and I'll be back. Here we are on the bench. So a whole day has passed. For me, it's the next day. This is day 2 of recording my little adventure into Epaper or e-ink. This is my WeAct Studio Epaper module that I'm figuring out how to use. Earlier in this video, we plugged the adapter cable onto the back here of the module. This is what it looks like. This is the 2.9 inch variety. There's 2.1 inch that I have as well, and there are some other form factors, smaller and larger, that I don't have. I have successfully loaded some software onto this thing using the Arduino IDE. There seems to be a little bit of a problem. It seems to crash after it loads the software in. So that's not going to really stop me if I can just then reset it. I'll see if I can show you what happens if we plug this in at the moment. There we go. So that that quick flash on and then the long flash off, that was me. I did that. It's a 100 millisecond delay followed by it's a 1 second off and then a 100 milliseconds on. Anyway, the point is it worked. I was able to upload the code to this. So the next thing to do is load the software that writes a message to the screen. So in order to test that, we're going to need to attach the screen to the module, to the microcontroller. So I'm planning to use the pin headers that it came with, and I'm going to feed them through to the bottom and solder them on the top in a similar fashion to how this one's been done. You see the board's on the top and the pins are on the bottom. This is an Arduino Nano for a separate project that I was working on. What I'll do is I'll get another breadboard like this and we'll do basically the same thing, except for this one we'll be connecting it to here instead of an OLED like this is. So I'm going to need the soldering iron on. Let me find out where that is. down here, iron on. Okay, it's set at 350 degrees. I'll put a little bit of water into our sponge. I don't know if we're going to need much water, but we'll have a bit of water in the sponge. So, where's some solder? Here's some solder. Good long length, that'll probably get us all the way through to the end. Now, I haven't actually done this before, soldering pin headers onto a microcontroller. I guess usually the ones that I buy come with the pin headers soldered on. I have to say I am happy to do a little bit of soldering though. I don't mind a little soldering job. I suppose if I was manufacturing things I'd feel differently about the work, but in this case I'm quite happy to just plod along, doing a bit of soldering. There we go. So I suppose I should just do each end and then tidy them up. So it says my iron's warm. Looks okay to me. Alright, I might even actually I might try my magnifying glass for this one. Let's see. This is my magnifying glass. Just goes on my face. Alright, let's see. Yeah, that looks pretty good. Alright. It's not going very well at all. I think what we need is some flux. I'll throw my fans on as well. Now, this is Antec flux. If you don't have this stuff, it's really great. It smells excellent. I know that's a bit of an odd thing to say, but it just smells yummy. You want to eat it. Well, we're going to need to give this a good clean after because I got flux everywhere. I have to say, this solder is not taking to the pads at all. It's really not working out for me. I'm not sure why it's so difficult. I'm going to try increasing the temperature on my iron a little bit. I've put it up to 380 degrees Celsius. I have been warned not to go over 365 degrees Celsius, so I have a feeling this is not, I don't know, it just, I don't feel like I'm getting the full amount of heat here. I'm not sure. Hmm. Dear me. I got some Q-tips. These are for cleaning, they're not for ears. Although it probably wouldn't matter much. This is some isopropyl. It's not water. I really wasn't expecting to have this much trouble with the soldering. I suppose I'm going to need to try and buzz it out. I'll turn on my bench multimeter. It's got some clips, very good. Let's put it into continuity mode. Okay, the beeper is on, so this should beep. Yeah. Alright, well, might just clean this up a little bit before we continue. Alright, well, this won't test to see if it's connected to the board. What a nightmare. What am I going to do? I wonder if I should change the tip on my soldering iron. Maybe. I'm gonna apply flux again, and I'm gonna put the heater up to 400. Alright, I'm going to put it right up to 400, which is really high. And then if the tip burns out, I'll replace the tip. It's up to 400. Might just also give this a bit of a twist to make sure it's on nice and tight. Okay, well, hopefully that's tight. Alright. You know, if I have to do this again, I'm going to sand or lightly use a light abrasive on the pads. Yeah. I hope I'm not destroying it with the heat. Hi. All right. just going to cut some of that melted plastic off. All right. Well, I'm not really sure how I've fared, but the only thing to do now is plug it in and see. So, here is the breadboard. Now I'm going to put it in on this side. Alright, well, we'll just push him in. Might actually use it this way around. I was expecting it to go further in. Not sure how much force I want to apply. There we go. Alright. Well, now I need to go and figure out which pins to attach. So, alright. I'm just going to go and read the instructions. I'm going to wire this thing up. So, busy. Busy 3. Busy. Let's do it from the back. I'll do it from the top. res 2. DC 1. DC 1. Alright. CS 7. SCL 4. SCL 4. And I just jiggle these a bit. Alright, SDA 6. SDA 6. Okay. SDA 6. Ground. There we go. Ground. Ground. And VCC. Are we going to give it 5 volt or 3.3 volt? Alright, let's flip him over. Alright, take him out, in. Alright, well I'm having some trouble compiling the code for the 2.9 module, so I thought I might give it a go with the 2.13 module. Right. Well, if they're the same, busy res DC CS SCL SDA ground VCC. Alright, well they seem to be the same, so I'll get myself a little screwdriver here and I'll try and pop this out. Okay. Alright. Alright. So we've got our 2.3 module. Now, plug him in there. Alright, now we'll try and upload the code from that module. Well, I'm wiring in my logic analyzer, so let's see how we go doing that. Okay, so I'm going to call that a wrap. In this video, which I recorded now weeks ago, I had a go at getting my Epaper module to work. I didn't succeed. We had a look at the data sheets. We set up Arduino, installed the right libraries. We set up our ESP32-C3 with the pin headers that were required, and then we began down the path of using the logic analyzer to spy on the serial line to see what's happening, but that's as far as we got, and I'm just going to tie this off here. So we're done for this video now. It was not mission accomplished, but I'm gonna revisit this topic in the future, and I'm gonna have another go at these Epaper modules. And so you know, if you're interested in that, you know, stick around. So if you made it all the way to the end, I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.